All right, folks, in this video, we're going to talk about rational exponents and radicals, right? We've already talked about integer exponents or integral exponents. Now what we want to do is switch gears and look at when our exponents have fractions. All right, so remember, any rational number is a number that can be written as a fraction. So these words are kind of like synonyms here. And then we're going to define what radicals are. All right, so we're going to actually start with the radicals. Another word for radicals is roots. The principal square root of a positive integer a. We use this notation here, the square root of a. So I'll usually use the word square root, although I mean principal square root, all right? Look at this symbol. It looks like a division symbol with a check mark out front. That is called your radical sign. And there's a number understood to be here when we don't see a number. It's actually a 2 understood to be there. And let's say that we knew what this equal. I'm going to say that this equals b. Then the principal square root of a equals b means that there exists a number b such that if I square it, I get that number under that radical symbol. All right. Now this a is called your radicand. This 2 here is called your index. And then that root symbol is your radical. And so basically we're finding the number such that if we square it, we get the number that's under the radical. All right. We not only have an index of 2 here, but we can have any positive integer greater than or equal to 2 as our index, right? And so this is what we're using for the nth root of a. The nth root of a equals b. All we're doing is finding the number b such that if I raise b to that index, which is n right here, I'm going to get what I started with in my radicand, all right? And so let's look at a few examples of that, right? In part A, we have the principal square root of 49. We have to find a number that if we square it, we get 49. Well, that number is 7. So the principal square root of 49 is 7. In part B, we have the principal square root of negative 49. I'm sorry, one of my colleagues is doing some work. So sorry if you hear that. The square root of negative 49, we got to find the number such that if we square it, we get negative 49. Got to think, we're working in the real number system. If I multiply a number by itself or I square a number, hey, I'm always going to get a positive result. So these are not always, they don't always have a real outcome, right? Now we're going to be working in the real number system, and we'll see that when we're solving equations and things of that nature, we may get some complex numbers or numbers that are not real numbers. That's the case here. This is not a real number. It equals a number, but it's not a real number. And so I'm just going to leave that there. If you really want to know, that's equals 7i, where I is the same thing as the square root of negative 1. We're not going to focus too much on imaginary numbers or complex numbers in this class, but I'm sure some of you have seen that before. All right, let's go to part C. It's the negative of the square root of 49, right? Or the opposite of the square root of 49, right? So we first start with the inside, right? Under the radical, there's a 49 under my square root. I got to find the number such that if I square it or multiply it by itself, I get 49. That number is 7. And this negative out front says to do the opposite of that 7, or the negative of that 7. So my solution here will be negative 7. Part D, we have a cube root, right? Now index, remember we use that term index there, that index is 3. So now instead of thinking about the number that we square to get this radicand or 64, we look for the number that we cube or multiply 3 times by itself to get 64. And that number actually is 4. Part E, I have the cube root of negative 64. Now when we were dealing with the square root, we saw that this was not a real result. It's not a real number. However, when our index is odd, like this 3 right here, notice if you multiply a negative 3 times, like negative 1 times negative 1 is 1, but if I multiply that by another negative 1, that's a negative 1. So I can multiply a number 3 times by itself and get a negative result. So this is actually going to be a real number. And in fact, if I multiply negative 4 3 times, I'm going to get negative 64. So my cube root of negative 64 is negative 4. For our F, we have a fourth root. Uh-oh, now we're back in the case of having an even index. My index here is 4. And just as was the case with the square root, this is not a real number. Because if I multiply a number an even number of times, I'm not going to get a negative result if it is a real number. And so one of the things that you want to remember is that if the index is even, then the radicand must be positive. So the number that's under the radical must be positive to yield a real result. And if the index is odd, then the radicand really can be positive or negative to yield a real result. All right, so that's a good introduction to radicals. Let's talk about rational exponents. All right, rational exponents are fractional exponents. They are defined to be equivalent or equal to radicals, right? And so let's say I have a number a that's raised to the 1 divided by n exponent, 1 divided by n. That is equivalent to taking that n, which is the denominator of that fractional exponent, and making it the index of your radical. So a to the 1 over n is the nth root of a, okay? This is the definition here. It's what we accept as fact. Over here, let's say that there's a number other than 1 in that numerator of that exponent. So I have a to the m over n. All right, one of the things that you can do is, okay, I could write this using my power rule from, our power of a power rule from rules of exponents. I can write this as a to the m times 1 over n. And I can kind of unsimplify that and write it as a to the m to the 1 over n exponent, right? So I'm kind of unsimplifying a power of a power rule, right? Well, if I write that this way, then by this rule over here, we see that, oh, I can take that 1 over n and make that my radical, right? The denominator would be my radical, so I get the nth root of a to the m, right? And so that's what this equals. Notice here, I did this, well, multiplication is commutative, right? Which means the order in which we multiply does not matter. And so instead of writing this way, what I could do is say, oh, I'm going to do a to the 1 over n times m, all right? And if I undo the power of a power rule, then I get this radical right here. So we could also write this as the nth root of a, all of that to the nth power, all right? Sometimes I like to write it this way. Sometimes I like to write it that way, depend on what I'm doing. And so be careful there when you do that, all right? Or be careful to, not be careful, but you have a choice there. The choice is yours based off of what you want to do. And so let's look at some of these examples here. I have 4 to the 3/2 power. I want to evaluate this expression. Now, remember your radical, your rational exponents, excuse me, are equivalent to rational expressions, radical expressions. And so what I'm going to do is I'm going to rewrite this using radicals, right? Now, I have this as a 3 over 2. So I'm in this case over here, right? So I'm going to write it using, well, let's do it. We're going to do this example both ways, and I'll show you which method that I would rather use, right? If I do it this way, then I'm going to have this equaling the square root, I don't have to put a 2 there, of 4 to the 3rd power, right? The square root of 4 to the 3rd power. Well, by my order of operations, I'm going to work inside this grouping symbol, which has a power or exponent. So this is the square root of 64, and the square root of 64 is 8, all right? An alternative way to do it is to write it this way, okay? So what I'm going to do is I'm going to write that as the square root of 4, and then I raise that to the 3rd power, right? Same thing. Index 2 is in here, but I wait until raise this to the 3rd power after I do my radical. And so the square root of 4 is 2, so this is 2 to the 3rd power, and 2 to the 3rd power equals 8. All right, I prefer this method here because sometimes this number right here may be big, right? So if I had something like 16 to the 3/2, well, if I did it this way, I've got to figure out what 16 to the 3rd power is. I wonder if you guys can see that. Yeah. The square root of 16 to the 3rd power, I first have to see what 16 to the third power is, right? And in this class, I don't have a calculator, right? And so I don't want to necessarily do it this way. It may be easier for me if I did it the opposite way of doing the square root of 16, figure out what that is, and raising that to the third power. My numbers are a little smaller, okay? I'm going to save part B for you guys to do on your own so that this video won't be as long as it can be. And so I'm going to move on to the next topic of looking at roots of variable expressions, all right? Now, I have the square root of x squared here. Remember from, well, let's do some math here, right? Let's figure out a pattern, right? This is x squared to the 1/2 power, right? Because the square root here means raise it to the 1/2 power. Well, here we have a power to a power, which means we get x to the first power, which is just x, right? Now, because this is a square root, this is a principal square root. We only deal with principal square roots in this class. And so what we're going to do here is since we have a variable, we don't know the value of x. But I know when it's under this radical, it's going to be squared. So if x is a real number, that's positive. And what we said was that if we do the square root, it has to be of a positive number, which x squared is. But since we don't know what x is, x squared is under that radical, we don't know what x is, we have to use an absolute value in order for this to be an accurate principal square root, all right? And so that square root of x squared actually equals the absolute value of x. Most people remember this, not a lot of people remember that, all right? Let's go to the cube root of x cubed. The same thing happens, right? Or a similar thing happens at the beginning, right? If I wanted to rewrite this, I can write that as x cubed to the 1/3 power, right? Well, I multiply those exponents, I get x to the first power of just x. Now, this is a cube root, right? This is to the third power. With an odd index radical, we don't need whatever is under that radical to be positive or negative, right? We just wrote that down up here. If the index is odd, then the radicand can be positive or negative to end up with the real result. And the real result can be positive or negative. And so since this can be positive or negative, I don't need an absolute value here. So that's going to be x. The fourth root of x to the fourth power, again, like this even index here, this is going to equal the absolute value of x. And since this is odd, this is just going to equal x. And so to sum that up, if our index n is even, then the nth root of a to the n is absolute value of a. And actually, this is a variable, so a equals a variable. Okay? A variable expression. I know above, I want to be clear, above we used a as a real number, right? If a is a variable expression. All right, and then here, the nth root of a to the n is just a if the index is odd. So if I ask you to find out what the square root of x squared equals, that's absolute value of x. Or if I ask you to take the square root of 16x squared, that's 4 times the absolute value of x. The square root of 16 is 4. The square root of x squared is the absolute value of x. All right, that's how we simplify that. And so what we really want you to be able to do here in this section is to be able to simplify radical expressions, all right? And there are a lot of tools that we already have developed in order to help us simplify any arithmetic expression. Those methods include things like the order of operations. You also have your rules of exponents. So all of those rules of exponents that we went over in the last video, they still apply to radical expressions and fractional exponents because they are exponents themselves. We're also going to add the product and quotient rules, which we've already seen with rules of exponents, but sometimes, it's good to see them applied to radical expressions, right? And so we have a product rule, right? If we have the nth root of a times b, right? That's a product under that radical. Then what we can do is we can do the nth root of each of those factors in that product separately. And so we can write it as the nth root of a times the nth root of b. This basically comes from our power rule power of a product rule from before, right? If we have a times b to the 1 over n, I just wrote this expression using fractional exponents. That's a to the 1 over n times b to the 1 over n. And if we wanted to write that back in the radical notation, that's the nth root of a times the nth root of b, right? And the similar thing happens with the quotient rule. The nth root of a divided by b is the nth root of a divided by the nth root of b. And it follows this same pattern, but with division. So you can use these rules to help you simplify. In addition to simplifying that way, when we're given a square root, right? The square root of 25 equals 5. The square root of 36 equals 6. The square root of 100 equals 10, right? Those are perfect squares, right? Well, what is the square root of, let's say, 92? Well, it may be an irrational number, but we always want to simplify these as much as possible, okay? And so these are the three things that I always like to tell my students to do, or check and see in order to determine if your radical is in simplified form, all right? In simplified form, your radical can have no perfect numbers as factors of your radicand, right? And perfect numbers are like perfect squares if you have a square root, perfect cubes if you have a cube root, or perfect fourths if you have a fourth root, so on and so forth, right? And so if any of these numbers, if you have a square root and any of these numbers divide evenly into the number under your square root, you need to factor those and take the square root of that part of your radicand. Same thing goes for your perfect cubes, perfect fourths. I wrote these numbers here because it's good for you to get very familiar with these numbers, all right? There can also not be any fractions in the radicand when your radical is in simplified form, and there should be no radicals in a denominator when your radical is in simplified form. And this last piece, we go through a process called rationalize the denominator in order to remove radicals that are in your denominator, all right? So putting all that together, we're just gonna look at a few examples, and then we're gonna end this video. So we're gonna simplify each expression, and we're going to use absolute values if necessary, all right? Now, here I have x to the 10th to the 1/5. Notice whenever I have fractional exponents, I'm always going to pay attention to a denominator, all right, to determine whether it's even or odd, because I may have to use absolute values, right? So remember, when the index is even, the absolute value of the even radical is going to involve an absolute value. If it is odd, it is not going to involve an absolute value, right? So I have a 1/5. This is equivalent, you don't have to necessarily write it this way, to saying the 5th root of x to the 10th, all right? These are equivalent things. Since this index is odd, I'm not going to have to worry about absolute values. Now, if you look at this, this looks like a power of a power rule, right? Where it says that, oh, I can multiply that 10 by that 1/5, and I get x squared, right? 10 times 1/5 is 2, so I get x squared. All right, now had this index been even, all right, I probably wouldn't get this number, but I could potentially have to use absolute values. However, if you look at this, this is x squared, and if x is a real number, if I square it, it is always going to be positive. And so if you think about this one here, you probably would never have to use absolute values. It is not necessary because you got a square. However, if that was not squared and if this was even, you would need to put this in absolute values, all right? Let's go to this example here. I want to be specific, and I want to use this rule that we wrote up here, the product and the quotient rule. It's just saying that, oh, I can look at these separately. So I can do the 4th root of 16, the 4th root of x to the 4th, that's a 4 there, times the 4th root of y to the 8th, right? And if I look at these separately, what number do I multiply 4 times to get 16? That number is 2. The 4th root of x to the 4th, oh, that was in my chart up here. That equals the absolute value of x, because I'm going to have to use that absolute value because that index is even. So that's the absolute value of x. I have the 4th root of y to the 8th. Okay, well, if you think about this, this is y to the 8th raised to the 1/4 power, which is, well, 8 divided by 4 is 2, y squared. Notice I would have to use absolute values, but I want you to be careful here. I mean, and this is not very important that you do, but notice here, this is a y squared. So no matter whether I get a positive or a negative y, this expression is going to be positive, right? Because it's squared. If I multiply a number by itself, we get a positive result. So you don't necessarily need that y squared in absolute value. So I could write my solution here as the absolute value of x. A little shortcut here when we're dealing with this, just divide your power under your radical by your index, and that'll give you simplified form, because that's exactly what we're going to do here. So like I did this 8 divided by 4, I get 2, same thing, all right? Let's look at some expressions that just involve numbers. I have the square root of 72. 72 is not a perfect square, but what I want to do is I want to find the largest perfect square that divides evenly into 72. Well, if I go back up, oh, 4 goes into 72, right? If I did 4 into 72, 18 times, right? But if you look at that 18, 18 has a factor of 9 in it. So if a number has a factor of 4 and 9, 4 times 9 is 36, right? So 36 goes evenly into that as well, right? We can write 72 as the square root of 36 times 2. Now, that product rule says I can do these square roots separately, right? And the square root of 36 is 6 times the square root of 2. And so this is in completely simplified form. Let's look at the the cube root of 128. Well, now I have an index of 3, and 128 is, let's go back to that list of perfect cubes, 128 is not on there. So let's see if 8 goes into 128. It doesn't. Does 27 go evenly into it? No, I don't believe so. But 64 does. And so we can write the cube root of 128 is 64 times 2. The cube root of 64 is 4. And I can't simplify the cube root of 2, so it stays the cube root of 2. This is in completely simplified form. All right, part C. We have a radical in the denominator. That is not considered simplified. And so we have to rationalize the denominator. Now, there's a whole thing that a whole spiel that I can go about in talking about rationalizing the denominator. We're just going to look at when there's a single radical in the denominator. And so what we're having here is I want to change this to a number that is a rational number. And in fact, we want it to be an integer. In fact, we want it to be a whole number, all right, if you want all the facts, all right? We want it to be a natural number, actually. And so the way we're going to do this is to use the fact that if I multiply a square root of something by itself, right? The square root of 2 times the square root of 2, I can write that as square root of 2 times 2 or 4, which is 2, right? And so what we're going to do is we're going to be smart, and we're going to multiply the numerator and the denominator, because this is a fraction, by the radical that's in the denominator, all right? Now remember, when you multiply across if nothing cancels. So 3 times the square root of 2 is 3 square root of 2, and the square root of 2 times the square root of 2 is 2. This is actually simplified. It looks more complicated than this. However, dividing by an irrational number causes some problems. You're dividing by a number that doesn't have a final decimal place. All right. And in part D, we have a fraction here in our radicand. So I'm going to separate it into 2 separate radicals with that division by using that quotient rule that we wrote above. And now I'm back in this case over here where I have a radical in my denominator. So I'm going to multiply by the radical that's on the numerator and the denominator, then multiply across. The square root of 7 times the square root of 5 is the square root of 35. The square root of 5 times itself is just 5. And that is all for this video.